Alright guys, this is 2B or not 2B. 2B. Okay, we're going to look at different types of energy now. In the first part we talked about how basic chemistry works, how biological molecules can be put together. We talked about those macromolecules. Now we're going to look at how energy can be stored in those bonds a little bit, and then we're going to look at various types of energy sources. So I'm going to kind of tease a little bit of like the latter part of the year into this lesson, just so you can familiarize yourself with different types of energy. All right, and we're going to look at, where those energy things come from, but then the trouble and the problems we have with trying to keep that energy within a closed system, and how hard it is to keep a system actually closed, right? So we're going to look at types of systems. We're also going to look at loops, feedback loops, right? Positive and negative feedback loops, all right? So what is this idea of energy, right? So if I don't eat, I cannot go to work, right? If you think about that, like the energy I need to go do work is in my food, right? So the energy that food gives you the ability to do work, and this is a physics definition that you should remember, or now it's something that you know a year ahead if you're in chemistry right now. All right, a joule is how we measure energy. It's the unit of work and energy, right? That's why we have this thing called the work equals the change in energy, the work-energy theorem. So the amount of work I do on an object should be equivalent to the change in energy on the state of that matter, right? So if I lift something up in the air, right, the energy I had to put into that object changed from this height to this height, and now it has a higher gravitational potential energy, right? Or if there's an object that's sitting still, like this arrow right here, and then I apply some sort of force to it for a period of time, it'll accelerate, right? And that's a change in energy. That's a kinetic energy. Okay, so there are different types of energy, and we're going to kind of show how human beings take advantage of those energy, and they put it to work, right? So it's worth noting that this idea of putting work into a system to change its energy also works the other way around. I can use energy and convert it into work that is useful for human beings. Okay, then we have this idea of power, and it is the rate at which work is done, right? This is work times time, right? Work, or power, is work over time, right? So the rate at which work is done. Okay, all right, and we'll be doing calculations with these guys right here. We'll do a lot of power calculations throughout the year. I'm not going to make you memorize a lot of these. You'll get a lot of these conversion factors if you're ever asked to. If you're ever asked to on a test or something, you'll usually be given some of these conversion factors. I'd be shocked if you weren't. But you do need to know the prefixes. You do need to know these prefixes, these kilo, milli, centi, like those common ones are very important. Mega, let's see, what's another one? Yeah, mega, micro. Those are the important ones. So the ones that you're learning in chemistry, it'd be good to remember them now. But you do need to know that a calorie is a one-to-one sort of thing, right? And we'll do calculations with these, and you're going to use this, guess what? The amount of energy it takes to heat 1 gram of water 1 degree Celsius. So you have a conversion factor here. This is 1 gram equals 1 degree Celsius per 1 calorie, right? That's little calorie versus big calorie. Big calorie is 1,000 little calories right here. This is something, if you ever do nutrition, this is one of those trivia questions they like to ask you. All right, here's some common uses of it. It's kind of interesting stuff. We're going to be doing a lot of our math calculations in kilowatt hours. Just keep in mind that a watt is a unit of power, but usually your power usage at your house is done in kilowatt hours. So very important. You may not understand this right now, but I want you to write it down, that every time you have some unit of energy, like kilowatt, you always need to add a time to it as well. So we're always going to do our calculations in kilowatt hours or watt hours. A lot of the times it's going to be both the kilo. We're going to do kilowatt hours with everything, so make sure you star that. All right, so how do we find energy in the universe? There is electromagnetic radiation. We'll teach you that a little bit further down the line, what the electromagnetic spectrum looks like. It is a form of energy emitted by the sun that includes, but not limited to, visible light, ultraviolet light, and infrared energy. You also have radio waves, you have infrared, you have microwaves, X-rays, gamma rays, right? So those are some of the other ones there. And within that entire range of the electromagnetic spectrum, it's worth noting that visible light, the stuff we see, encompasses a very, very, very small wavelength range within that entire thing. So imagine if we could see the universe in infrared and ultraviolet, and we could experience gamma rays. Well, you can experience gamma rays. It's just not very pleasant, right? But I mean, you can't see them with your eyes, though. And that's unfortunate. Some animals can. Some animals can see things beyond what human beings can comprehend with their sight. All right. So within that visible light spectrum, there are these things called photons, right? They are massless packets of energy that carry electromagnetic radiation at the speed of light. If they had any mass, they wouldn't be able to travel at the speed of light. But this right here, this very fact that they're massless and they travel at the speed of light from the sun, for the purposes of what we're talking about, is kind of like the key to the future for us, right? If we can figure out how to take advantage of the fact that we basically have an inexhaustible source of energy that just flies at us at the speed of light, we can solve most of our energy crises and along with it a lot of the environmental problems we're having with our fuel sources we're using now. And I'm not just talking about fossil fuels pumping carbon in the air. I mean, we're talking about people that live in third world countries or they're low to medium developing countries that are having to use things like biomass, like animal poop and charcoal to heat their houses and light things. Now imagine if they could harness the power of photon energy at will, right? Everything, and I mean everything is powered by the sun. So you need to write that down. Everything is powered by the sun. Maybe not directly, maybe not today, maybe not yesterday, but at some point in time, the source energy for everything came from the sun, okay? With the exception of maybe geothermal energy. Yeah, geothermal energy. That comes from the inside of the earth, right? But everything else other than that is going to be from the sun. Okay, now let's break down energy into different types of mechanical energy. So right here, the potential energy and kinetic energy. These are forms of mechanical energy, and it's the total energy in a system. And chemical energy is just potential energy on a really, really small scale, right? Potential energy is energy that is waiting to be released, right? And that could be a rock on a cliff. That could be something like chemical energy, like gunpowder that's waiting to be ignited, right? So these are all different types of potential energy. Kinetic energy, on the other hand, is the opposite. It's the energy of motion. That's that rock that is kicked from the ledge and falls to the ground. But it's also some of these things. All right, let's take a look at some of these. So here's some examples of kinetic energy, right? Kinetic energy being turned into, let's move this stuff over here. There we go. So here's some examples of kinetic energy being turned into stored energy, stored potential electrical energy, right? So some people have always joked about, yeah, let's just power the entire city with people on treadmills. The problem with that is that most of these machines here are just powering the machine that people are working on, right? And it is incredibly hard to keep even a small watt light bulb burning with a hand crank, right? Well, if you've ever played with those little hand crank generators in physics, as soon as you connect a light bulb to them, they are not very, very easy to turn. I mean, you're a big, strong human being, so I mean, they're easy relative to the size of the bulb, but it's definitely not an easy task to do forever, right? So this is kind of like a little funny thing, you know. I always imagine like hamsters on a wheel, and if we could just get all the hamsters in the world and connect them to the grid, we would power, you know, a very small LED or something like that. It'd be amazing. Okay, here's a more practical way that we convert kinetic energy from nature into stored electrical energy. These are windmills, and some of these windmills are obviously not for energy. They are, you know, things that are like drawing water out of the ground and everything like that. But these windmill arrays here that they have, usually in bare places that aren't going to soak up all the wind, can get some of the kinetic energy that comes through and store it into some generator down here. And you're going to want to know how that works, right? You're going to want to know how that process works of storing mechanical energy and converting it into electrical energy that we can store for later. Okay, let's see. Let's look at another one. So here's some more. Here we go. Tidal. Let's see. Hydroelectric. Let's see if I can. All right. Here we go. So hydroelectric, so this is taking advantage of potential energy. The water is up here at some certain height, and then it drops down and it turns some sort of turbine here in the middle and spins it, and that potential energy turned into kinetic energy here, turned into kinetic energy of some wheel or turbine down here. And it does some stuff that we'll talk about later with electromagnetic fields and coils and generators and all that. But you need to know that nature does this all the time, and human beings are ingenious enough to take advantage of that. This is another one of those things that obviously doesn't have a lot of apparent CO2 emissions. So it's something that a lot of people look to for an alternative to coal and natural gas and petroleum. But this too also has its own ecological problems that we'll talk about in the future. Okay? Okay, over here we have, this is a really interesting one, tidal energy. So the tides go in, tides go out, and I actually can explain that. So check it out. The tide in the morning is different from the tide at night, and that change in the water level will end up having some kinetic energy transfer from potential. See, the water up here is a certain height, and as it drops, it'll gain some kinetic energy and spin through this turbine here. All right, so this is something that is hard to do all over the world, because even though we have lots of coastlines in Texas and California, this is only as effective as the difference in height from day to night, right? So if you don't have something with a very drastic height from day to night, it is not a very effective way to harness energy. So I think places like in Iceland and in South Korea, which have tidal differences in some places up to 13 feet, can make good use of this. But otherwise, it's not very practical anywhere else. Right? There's some other things people can do, like maybe put some turbines underwater, right? Kind of like the way that windmills work, but underwater, right? Okay. Now we get into potential energy, or the potential chemical energy here, petroleum. What you need to know about petroleum is that, for everything that we say about it, it is a very high quality energy, right? For the volume that we use, it has one of the highest outputs of energy. It's what makes it so difficult to transfer over sometimes to battery powered, right? Because batteries are very heavy, and they use a lot of precious materials and have a lot of ecological problems of their own. And right now, oil is still relatively cheap, and it's very energy dense for what it does. So it's something that you can have a discussion about, right? Okay, over here, let's see. Natural gas is kind of what people have been all the rage about in the last few decades, because they say things like it's cleaner, it has less emissions, but really what we're going to learn in this class is what type of emissions people are talking about. It can really change the conversation and how you feel about it, right? And these have the problems of their own, but again, this is one of the things that we also do with petroleum, right, or natural gas rather. Right? And fracking, you need to associate natural gas with fracking, right, for extraction. Right? There are other ways to do it, but right now we're using a lot of fracking for it. Okay. This is solar energy, right? These solar arrays here. China is in the lead right now for solar panel production and solar technology. So it's something that we need to think about. So I always thought we were number one, so let's do that. Now, we've been talking about stuff you're probably at least relatively familiar with the exception of maybe the tidal power. But here are some things, like if you live in a different country, you may have to consider doing for energy source, right? So we're all familiar with charcoal when we go barbecue, but you usually don't use this to heat your house. You usually don't use this to cook your food all the time, right? But imagine if you were somewhere that it didn't have an electrical grid, you didn't have solar panels, you didn't have good enough infrastructure or public services that could finance hydroelectric dams and windmills and things like that. You would have to resort to something more like this. This is biomass. Okay, this is biomass. Basically, you're just getting things that can burn. This is potential energy in here. When you hit its burning point, its flash point or whatever, it will release energy in the form of heat. Right? This is very inefficient, and it has a lot of very localized pollution that can be very harmful to people, right? But these are the things that people have to make decisions on in order to survive, right? But this is also potential energy that is released. Okay, then we take those ideas from the developing nations and we try to make sustainable ones through biofuels, using corn, using sugarcane, using soybeans, sorghum, right? And they're also trying to hybridize different things together so that they're easier to harvest. So this is kind of a broad overview of what energy chapter is going to look like for our sources. I obviously left out a few because they can get pretty exhaustive, but nuclear energy is another option as well. Laws of thermodynamics describe how energy behaves. Basically, thermodynamics is super important. It was one of the most significant principles in all of science, and it tells you why we have problems with energy, and it starts from the beginning. It starts from the source, from where we get our energy from, and how readily we can absorb it. How easy is it to absorb every single photon of light that hits the surface of the Earth? Right. So that is part of the issue with our energy crisis in a way, because it's just we're screwed by physics. We're screwed by physics essentially. All right. No. Okay, now this picture, I kind of want you to see it a little bit differently than it's showing here. The first law of thermodynamics is that energy is not created or destroyed, just like conservation of mass in chemistry. All it does is it transforms into one form of energy to another, and I don't want you to think that this car is being wind powered, right? So there is not wind coming in, powering the engine, and then shooting out through the exhaust. What's happening here is there's more like the chemical energy stored up in the gas tank, just back here actually, goes into the engine here, gets exploded. That chemical energy is released into heat energy, which powers a piston. Now you got that heat energy being transformed into kinetic energy. Kinetic energy is driving the drivetrain, and the excess energy that is not able to be used because you don't have 100% efficiency in a system, that heat gets transferred to the engine block, parts of the car. If you've ever opened up the inside of a car, you would not touch the engine block or anything inside that's metallic, especially after it's been driving for a while, right? In fact, there are recipes online where you can put like something in tinfoil, put it on the engine, drive for like 10 miles, and open it, it'll be done. So that excess energy is going to go out through the exhaust, right? And the difference in energy that is kinetic, that drove the car, 1/2 mv squared, and the heat energy that's released is the total energy that was inside the chemical potential of that gasoline. All right, so that's the conservation of energy. It's not that you use 100% of it, but it's that 100% of it is always accounted for in some sort of system. All right, here's just another example of that. It's really interesting. Your incandescent bulbs, right, your non-fluorescents, are going to use only about 5% as useful light energy. The rest is going to be given off as heat, waste energy. But you can actually track that back from the power lines and then from the power plant that created that energy. You see a lot of that is heat. We're only getting 35% as it goes into the power lines. This is pretty efficient, but the longer the power lines go, if you remember like the laws, the Kirchhoff's laws, right? You remember Lorenz's laws for cross-section of wires and things like that? The longer the wire, the higher the resistance. So you're going to lose some of that as heat. So you can actually calculate this, and you need to know this as part of our math calculations for this chapter. This is how you would calculate this out. Okay? All right, we'll practice this chapter. All right, so kind of looking into the second law of thermodynamics a little bit more, we have this idea of entropy, which you need to know is essentially this idea of how messy something is, right? So if you leave a cup of coffee that's really, really hot on a counter for a while, what's it going to do? Well, eventually it's going to cool down. And I explained this a little bit in class yesterday because of the way that the molecules collide and rebound and bounce off of each other. They have a lower and lower probability after collision of finding another molecule ever again, right, as you increase the space and the volume, because you take a non-moving molecule, right, you take a non-moving molecule, like say right here, and you have a moving molecule that hits it from over here. It's going to split some of that kinetic energy, and now both of them are going to kind of go in different directions, but slower than the first one, right? So if the first one was moving really fast when they hit, now this one's going to move faster than zero, but this one's also going to move a little bit slower. And you notice that they're going to kind of move away from each other. If they hit something again, they're going to split that energy, maybe move even slower. So that's what happens with entropy over time. All systems tend toward disorder of energy. It takes a lot of organization to keep all that heat energy in one spot, right? So that's what happens over time. Now, the amount of energy you put into actually igniting something is the idea of like this energy efficiency, right? So the amount of energy you have to put into a system versus what you get out of it is this idea of energy efficiency. And when you're talking about burning fossil fuels or burning petroleum-based things, you start finding that things like coal are not as energy efficient as something like petroleum and not as energy efficient as something like natural gas. And those are not to say that they're not energy dense, right? So there's a high energy quality to those things because you get a lot out of them for what we put in, and that's why we've run off of fossil fuels for so long. Okay. All right. So we like to look at energy flow in the environment, and it kind of gives us an idea of either issues or how a system works. It lets us know whether or not a system is closed or open. All right, so this idea of open systems, exchanges of matter across system boundaries. So just kind of think about all the processes that you know about from chemistry. Think about all the processes you know about from biology and environmental systems you might have had in middle school and things like that. Things like evaporation, things like water cycles, things like reflection of sunlight, refraction, bending of sunlight. All those things are ways that show that systems can be open, right? If you're not talking about some hermetically sealed cave or some sort of terminal lake or something like that, you're gonna have an open system, right? If there's a way for water to get out, if there's a way for energy to seep out in some way, even if it's like animals flying away, that's an open system. The Earth as a whole, in terms of matter, is a closed system, right? It is true that we get a lot of extra material per year, a lot of tonnage worth of asteroids that hit the Earth and meteors, but for the most part, we're talking about a closed system for that. The energy, on the other hand, is open because the sunlight comes in, and I talked about how sunlight is really the source energy for almost all of our energy on the planet. But it reflects, right? So it's a little bit open, all right? Input and output, we do system analysis based on input and output. And when there is a balance of inputs to outputs, so energy coming in, energy coming out, we call that a steady state, and you're going to see that in the next slide. All right, so go ahead and take a look at that. We want our waste management to be kind of like this, right? So we're not creating excess waste in landfills, draining resources from the environment. Here we go. Here's a graphic. Here's an analogy of a steady state, matter and energy. All right, we got this idea of negative feedback loops. When something happens, it decreases some sort of state. And a positive feedback loop, change in the system is amplified. So a good example of this in the human body is with a negative feedback loop. The idea of getting really, really cold, right? The idea of getting really, really cold. So as your body gets cold, you trigger this response, shivering, right? Your teeth start chattering. So you have your temperature going down. You have your temperature going down. So your shivering goes up. And then what ends up happening next is your temperature goes up. So you had an opposite response to some decrease. So the negative feedback loop is the opposite, and then the result is that you get the opposite effect, right? Positive feedback loop in the human body would be childbirth. As the baby starts pushing against the cervix, it will trigger a release of oxytocin, which will increase the dilation of the female anatomy. The baby will push even harder because now it has more space to drop through the birth canal. It'll push more on the cervix, and guess what? It's going to put out more oxytocin. So this here is adding to the effect of the body, right? So that's a positive feedback loop. On Earth, when we're talking about Earth systems, the weather works in both ways, right? As we increase CO2, as CO2 goes up, guess what? The temperature, global temperature average will also go up, which will melt sea ice. It's over there. All right, which will melt sea ice. So again, you're going to end up with the CO2 increase, which will increase the temperature, right? So that's a positive feedback loop. Okay, I'll continue that more in just a second. All right, and here's the good stuff. Negative and positive feedback loops in apes. So these are the ones you need to know about. So if you're looking for a negative feedback loop, remember that negative feedback reduces the activity that's happening, so you can return back to whatever was normal, okay? Whereas a positive feedback loop is increasing the activity or event that's happening to amplify it, right? So when you think positive feedback loop, I want you to think amplification or increase, okay? and I want you to think of a negative feedback as a return to normalcy. Okay, so this is a return, right? Or a decrease in whatever the activity is. Okay, the activity, okay? All right. So here are the ones that they give you specifically. In negative feedback loop, they're giving you the level of water in a lake, and this is relevant to what we were talking about because we had a couple of case studies this chapter with Mono Lake and the Everglades, so we're talking about things that can happen. And I could tell a few of y'all today on your FRQ, because you had read this example, looking at you, David DeLeon, I could tell that you were able to say that one of the effects on the Everglades due to climate change was that the lake levels would drop. So that is a valid answer, right? You can say that the lake levels would drop because of increased evaporation from global climate change and increased temperatures. It is also valid to say that because of global climate change and water expansion, that the sea level will rise, and so the Everglade biome will be completely flooded and gone, right? And so it'll completely change what type of biome is there, right? So we look at the lake level. The level drops, so guess what happens? There's less surface area, and if you have ever tried letting a cup of water evaporate, it takes much longer than if you drop that cup of water on a tile floor because the surface area decreases, right? So that's very, very important. So as the level drops, the surface area decreases, and guess what's happening? You get less evaporation, and the level rises more, right? So this is something that's returning it back to normal, right? If you had the opposite effect, you would have more evaporation, right? Okay, so over here, positive feedback loop, the population increases. So guess what happens? More people can pair up and mate. I know it's kind of a weird way to say it, but there are more births, and guess what happens? Population increase. More births, population increase again. So we're going to learn about this later, but this is kind of like an exponential growth curve. So this is like the ideal growth curve. In reality, though, because of the limitations of resources, you end up with more of like a logistical growth curve. It's going to go exponential at first and then kind of level off as it approaches a carrying capacity here. Okay, yeah. All right. So these are the feedback loops that are good to know. And as we go through the year, we'll add more and more of these ideas of feedback loops to our arsenal of things that we can talk about, right? So these are really good things to talk about on FRQs. They'll ask you a little bit about like cascading effects and effects that happen as a result of some human activity or just some natural activity. Feedback loops are very good things to talk about in terms of connecting many different types of ideas together. All right, so that's 2B. So I hope that was helpful. Bye.